Let's start with our first topic, different types of concrete. Let's first see what is concrete. Concrete is the most commonly used man-made material on Earth, and also it is the most widely used construction material. When you look around, you can see many applications of concrete: bridges, buildings, roads, and dams. And also you can find many non-structural applications of concrete as well, like curbs, pipes, and drains. Here in this particular slide, you can see some examples. In the first figure, you can see a reinforced concrete building. You can see columns and beams constructed with reinforced concrete. And in the second figure, you can see a bridge built using reinforced concrete. And in the third figure, you can see reinforced concrete used to construct roads. There are many reasons for using concrete widely. We are going to discuss those in future topics. We said that concrete is the most widely used construction material. Let's see the reasons for using it widely. There are many positive aspects of concrete. The main reason for using concrete widely is its cost. It is a very economical material. Concrete is a composite material made up of cement, fine and coarse aggregates, and water. These materials are inexpensive and readily available compared to other construction materials. Also, concrete is an ambient temperature hardened material. When we mix cement and water together, they react at room temperature and get hardened and bond the aggregates together. So no higher temperature is needed. We can cast concrete into any shape easily. Fresh concrete is flowable as a liquid, so we can pour it into any shape of a framework. Concrete is an energy efficient material compared with steel. The energy consumption of concrete production is low. The energy required to produce plain concrete is only 450 to 750 kilowatt hours per ton. That of reinforced concrete is 800 to 3200 kilowatt hours per ton, but structural steel requires 8000 kilowatt hours per ton or more. Concrete also has an excellent resistance to water. Unlike wood and steel, concrete can be hardened in water and can withstand the action of water without serious deterioration. When we look at the heat transfer, concrete conducts heat slowly and it is able to store considerable quantity of heat from the environment. Concrete has the ability to consume waste from other industries. Due to the large amount of concrete produced annually, it is possible to completely consume most of industry waste in the world, provided that the suitable techniques are available. Instead of using aggregates, we can use industrial byproducts and waste in concrete production. For example, glass, polymers, and recycled aggregates. There are many research going on regarding this area. If you are interested, you can find more information in Google Scholar. Also, concrete has the ability to work with reinforcing steel. Concrete and steel have similar thermal expansion coefficients. So thermal expansions and contractions happens together as a single material. Also, concrete is an alkali material, so it provides a good protection to steel. As we all know, concrete is good in compressive forces but not with tensile. Therefore, while steel bars provide the necessary tensile strength, concrete provides a perfect environment for the steel, acting as a physical barrier. Concrete requires less maintenance. Under normal conditions, concrete structures do not need coating or painting as a protection for weathering, while for a steel or wood structure, it is necessary. Let's see the limitations of concrete. Concrete has quasi-brittle failure mode. When we consider the failure modes of different materials, we can divide them into three categories: brittle failure, quasi-brittle failure, and ductile failure. You can see the stress-strain curves of three different modes in this slide. Concrete is a quasi-brittle material that can exhibit a failure without yielding, so it has a low fracture toughness. It is good in compressive forces but not good in tensile forces, so we need to incorporate steel reinforcement in concrete. The quasi-brittle failure mode is explained more in this slide. Both brittle and quasi-brittle material fail suddenly without giving a large deformation as a warning sign. Ductile failure is a failure with a large deformation that serves as a warning before collapse, such as low carbon steel. Concrete is a type of coarse brittle material with low fracture toughness, as we discussed. So concrete has to be used with steel bars to form reinforced concrete, in which steel bars are used to carry tension and the concrete compression loads. Reinforced concrete is realized as the second generation of concrete. As we discussed before, concrete has low tensile strength. When we consider the tensile and the compressive strength of concrete, there are two different values. The tensile strength is only about 1/10 of the compressive strength for normal strength concrete, and it is lower for high strength concrete. But we can improve the tensile strength of concrete by adding fiber reinforcements and polymers. When we consider the toughness of concrete or the ductility, it has a lower value as well. We can find the toughness or the ductility of a material by the stress strain curve. The area under the stress strain curve gives us the toughness or the ductility. As you see in this curve, when we compare with steel, concrete has a very less toughness, but also we can improve the toughness by adding fibers. Concrete has a low specific strength. That means the strength to density ratio is less. For normal strength concrete, the specific strength is less than 20, while for steel it is 40. There are two ways to increase concrete specific strength. One is to increase the strength or else to reduce the density. Hence, lightweight concrete and high strength concrete have been developed. So you can see some values compared with concrete and carbon steel here. A formwork is needed for concrete construction. Fresh concrete is in a liquid state and needs formwork to hold its shape and support its weight. Formwork can be made of steel or wood, as you can see in these figures. The formwork is expensive because it is labor intensive and time consuming. To improve efficiency, we can use precast formworks. Also, concrete has a long curing time. The design index for concrete strength is the 28-day compressive strength. Hence, full strength development needs a month at ambient temperature. However, in our later topics, we are going to discuss the ways of reducing the setting time for concrete. The other limitation that we have with concrete is working with cracks. Even for reinforced concrete structural member, the tension side has a concrete cover to protect the steel bars. For example, if we take a beam, we have reinforcement at the bottom. So when the forces are applied, the beam will deform and we have a tensile side and a compressive side. So at the tensile side, the cracks will propagate and the protection will not be there after the concrete is cracked. To solve the crack problem, pre-stressed concrete is developed and it is also realized as a third generation concrete. Most reinforced concrete structures have existing cracks on their tension side while carrying the service load. Now let's see the types of concrete. Based on the variation in concrete materials and the properties, concrete can be classified in different ways. We can classify concrete according with the unit weight. We also can classify them accordance with the compressive strength and also accordance with the additives. Let's start with classification in accordance with unit weight. According to the unit weight of concretes, they can be classified into 4 categories. You can see them in this table. Ultra lightweight concrete, which has a unit weight less than 1,200 kilograms per meter cube. Lightweight concrete, which is in between 1,200 and 1,800 kilograms per meter cube of unit weights. Normal weight concrete is around 2,400 kilograms per meter cube of unit weight, and heavy weight concrete has more than 3,200 kilograms per meter cubes of unit weight. Ultra lightweight concrete can only be used to build up non-structural members. A lightweight concrete can be used to build both non-structural and structural members depending on its specified composition. Normal weight concretes are commonly used concretes in the construction for infrastructure and buildings. Heavy weight concrete is used to build some special applications such as laboratories, hospital examination rooms, and nuclear plants where radioactive protection is needed. Let's see how we can classify concrete according to the compressive strength. We can categorize them into 4 groups: low strength concretes, moderate strength concretes, high strength concretes, and ultra high strength concretes. The compressive strength, if it is less than 20 megapascals, we classify them as low strength concretes. If the compressive strength is in between 20 to 50 megapascals, we categorize them as moderate strength concretes. And if the compressive strength is between 50 and 150 megapascals, we call them high strength concretes. And if the compressive strength is more than 150 megapascals, we classify them as ultra high strength concretes. Low strength concrete is mainly used to construct mass concrete structures, subgrades of roads and partitionings. Moderate strength concretes are the most commonly used concrete in buildings, bridges, and similar structures. High strength concrete can be used to build tall building columns, bridge towers, and shear walls. Ultra high strength concrete have not yet been widely used in structural constructions. Only a few footbridges and some structural segments such as girders have been built using such concretes. We can add additives to the concrete mix to improve properties. Concrete can be classified into different categories according to the materials other than cement, aggregates, and water that are added into the concrete mix. So you can see some examples here in this table. If we add water-soluble polymers, we call them as MDF, macro defect free concrete, and we can add different fibers and we can get fiber reinforced concretes, and also we can add some small particles of densified, so we call them DSP concrete, and also we can have polymers in concrete, we call them polymer concrete. Fiber reinforced concrete is a type of concrete with fibers incorporated, as we discussed before. Macro defect free MDF concrete is a cement-based composite that incorporates a large amount of water-soluble polymer produced in a twin roll mixing process. There are 3 methods to incorporate polymers into the concrete: using the polymer as a binder, in pigmenting the polymer into normal Portland cement concrete members, or using a polymer as an admixture in the ordinary Portland concrete. Here with this one we are finishing the subtopic 1 and we are moving to the subtopic 2.